Hello everyone. We'll get going right away. I'm hoping that this lesson actually might not take too long today. I do have a few examples I want to go through, but feel that they should be pretty easy to follow, I hope. So we'll get started and see where it goes. So we're going to be looking at more rational expressions today and talking about how to simplify them and how to talk about restrictions. So slightly more advanced today with the idea here that sometimes you can't state the restrictions right away until you've actually factored the denominator as well. Yesterday we were talking a lot about factoring the numerator, but sometimes you're going to have to factor the denominator too. So in a case like this, hopefully you can see that whoa. That is not a straight line. Hopefully you can see that the denominator can have I believe 5x squared is the highest factor that can be factored out of those two. And that we'd be left with a 5 minus 6x, if I'm not mistaken. And now that we factored those two, that denominator into those two factors, we can now state our restrictions. So if we look at this first one, we started kind of talking about the case yesterday of what happens if your x has a power to it, but it's just as simple as if x doesn't have a power to it. If you have a scenario where you have 5 times x squared, now yes, there is a 5 here, but that 5 just gets divided out, because if you divide both sides by 5, it just becomes 0 anyway. And the way I always thought of it is, can 5 on its own turn anything into 0? And the answer is no, 5 is 5. Okay, so the 5 doesn't technically affect the restrictions in any way, but the x squared does. So, you just solve for x, which would be square rooting, but square rooting 0 just gives you 0 anyway. So if you have any variable with a power that's multiplying in the denominator, the restriction is always still going to just be x can't be equal to 0. Now, what about this scenario here? So we discussed the idea of what happens. I'm just going to make an example off to the side here. If you have a denominator with a bracket like this, it's similar to finding the roots, where you just change the sign of the constant and then divide by the coefficient of x, which would be 3 in that case. In this case here, they switch things around, where the 5 is second and the 6x is first. But it's the same rule. Take the, and I'll prove it to you off to the side in a second, but take the constant, change its sign, and then divide by the coefficient of x. Now the coefficient of x in this case is negative 6. All right, so it would become a plus 5 and a plus 6 there. So just to prove that to you, if we did it the long way algebraically, isolate x. So what I would personally do is probably send the 6x over to the other side, which would become positive 6x, leave the 5 on that side, and then divide both sides by 6. And as you can see, we get the exact same answer. So if you know how to find your zeros for quadratics, it's basically the same idea to find the restrictions. Okay? Now, at this step, now that we've stated our restrictions, we can start canceling things out, because everything is now factored. Everything is multiplying and dividing now. Okay, the main operations are all multiplication and division. So as soon as that happens, that 5 and that 5 cancel. This x and this x simplify. And our final answer would be 1 over x times 5 minus 6x with those restrictions. And as I was mentioning yesterday, factoring is going to become very, very important. You're going to have to be able to factor quickly and efficiently in order to be able to find your restrictions and to be able to simplify. So we haven't done trinomial factoring in a little while, but it will come back into play very soon. So let me just pause there for a second, as this was the first example today. Are there any questions or anything that I need to explain a little bit more in detail before we move on? Okay, seeing no questions appearing in chat, I'm going to assume everything is good. Does the answer have to be in factored form? The answer should be left in factored form, yes. Does it have to be? No. But if we're going to be factoring to find your restrictions and to simplify anyway, you might as well just leave it like that. I believe it is recommended to leave it in factored form, though. Just so you avoid the step of redistributing, right? Any other questions? I feel like you would have had time to write the question down if you had one, actually. So let's just move on, if that's okay. And if you want me to, I'll definitely come back. Let's do another one similar to that one. And maybe without as much writing when we go to find our restrictions. So I should probably erase that equal sign there. So what we'd want to do is factor the bottom. You can't do anything to the top, so we're just going to factor the bottom. In this case, I think 2x is the biggest factor, the greatest common factor. So we'd have 6 minus 7x left over in the bracket. And our restrictions from the first factor of 2x, which is actually just x, really, we get x can't be equal to 0. And I'm hoping that I don't have to show the long way anymore. It would be negative 6 over negative 7, which would just be 6 over 7. So x can't be equal to 0, and x can't be equal to 6 over 7. Pretty sure I did that correctly. At that point, the 4 cancels out with the 2, leaves a 2 behind. The x cancels out with the x, leaves a 1 behind. And our final answer would be 2 over 6 minus 7x in this case. No bracket needed at the bottom anymore because it's the only factor left. If you continue on in mathematics, folks, you'll constantly be amazed at how complex a question can start and how easy it can end up when you start to simplify. Okay, so let's take a look at this next one. And this is what I was talking about just a few seconds ago. You're going to end up with some quadratic scenarios where you're going to have to use your factoring skills to be able to, factoring of a quadratic, specifically a trinomial, to get the format you need to find your restrictions. So if I build my little tree, and I know a lot of you have different ways of factoring, so it just becomes a question as how fast can you do it, okay? What two numbers multiply to 6 and add to negative 5? That would be negative 3 and negative 2. So because this is a type 1 trinomial, I can just substitute those values directly into the brackets. Our little trick for factoring. Oh, sorry, those are supposed to be m's. That is a very common mistake. And now I can set my restrictions. So my restrictions are m can't be equal to 3 from this first bracket. If I substitute a 3 in there, I get 0. And m can't be equal to 2. Technically, I should have done it in order. Because I'm on my smartboard, I can easily fix that. But it doesn't really matter what order you write your restrictions in as long as they're properly listed. Okay? So I hope everybody can see where the 2 came from. And now, because the entire top, m minus 2, matches the entire bottom, m minus 2, you can actually completely cancel those two out simply because, and only because, everything is multiplying and dividing. That's going to leave a 1 behind. Okay, it's not a 0. our final answer is 1 over m minus 3. And 1 over m minus 3, if you remember, is going to be a 1 over x graph that's been moved over to the right by 3. Now, so at 2, something happens at 2, which probably is an open circle at 2, and then our asymptote would be our other restriction. Okay, so again, I'd be curious as to see what Desmos does in a case like this. I feel like I've checked this before on Desmos. I'm not sure. I think it does give an open circle at that point, but I'd have to double check. But that's why this equation was written this way. For some reason, there's an open circle. It is a 1 over x graph, but I have to show that open circle somehow. So that's what's happening. Are there any questions about that? Okay, I will continue. If there's any questions that you think of as we go on, go ahead and ask them in chat, and I'll try to make sure to answer them. So here's another example, and this time our quadratic is at the top. Now, the quadratic being at the top makes it very easy to find our restriction. Y can't equal -5. But I want to still be able to simplify that. So how quickly can you factor the numerator here? Well, two numbers that multiply to 25 and add to 10. And I'm hoping that I don't even have to write them down. I'm hoping everybody can see that it's 5 and 5, which makes that a perfect square trinomial of y plus 5 squared. And now, because I have y plus 5 to the power of 2 divided by y plus 5, one of those cancels out with one of them from the top. And we usually indicate it by just taking away 1 from the power, which becomes a power of 1 now. And the bottom is a 1, so this is just going to be y plus 5. So what kind of graph is y plus 5? Just to keep linking back to the graphs. If I graphed, and it's a little weird because usually y would be isolated on the left and we'd have x plus 5 as our equation, but this just means that y is the x-axis value, which is weird, okay? And we have some sort of unknown y-axis value for our variables. And that is correct. Y plus 5 is mx plus b technically, so this would be a 45-degree line crossing through 5, right? But at -5, which is the x-axis value, if I'm not mistaken, it took me a second there to realize, I think it's the x-axis value, or the x-intercept, there would be an open circle there. Oops, sorry about that. Made it a little bit too long. But yeah, there'd be an open circle at at y equals -5. On the this weird y-axis, okay? So that's why this equation had to be written that way, to show that there's an open circle at that spot. I think I've mentioned before, folks, the more you can visualize the graph from an equation, the more you can train your brain to understand that those two things are the same, the better you'll be at understanding math in general. Because graphs do help you kind of visualize how the function is behaving. And if you can make that link, which we did a lot of work with, if you remember way back in February when we did our special dance for our transformations of functions, it will help you to be able to do your math a lot more visually, I guess is the word I'm looking for. Okay, let's look at this one. So again, how quickly can you identify what type of factoring that we have to do here, and what kind of factoring do we have to do here? Now, yesterday we saw differences of squares pop up, so I'm hoping everybody can recognize that as a difference of squares. At the bottom here, what are we going to be able to pull out? Well, we can definitely factor out a 2, and we can factor out an x, and we can factor out a y. So just a quick reminder, for your variables, if they share all the same variables in all terms, then you can factor out the lowest power of each variable from all terms. So the x squared and the x, which one has the lower power? The x has a power of 1. So that's why I was able to pull out a power of 1 for x. And for y, both of them have a power of 1, so I'm able to pull out that power of 1. Now, what would be left over? In this position, I'd have an x left over, because it was an x squared. And in this position, I'd have a minus 3 left over, because the x and y are gone. And now I can state my restrictions. So my restrictions are x can't equal two numbers, 0 and 3. And y can't equal 0, because y is also just a factor all by itself. Therefore, if I replaced it by 0, the whole bottom would become 0. And we can't have 0 as our denominator ever. And after you've done that, x minus 3 has a corresponding x minus 3 on the bottom. Therefore, and because they are multiplying, we can cross them off, and that would be our final equation. Now, in this case, folks, I actually have no idea what that graph looks like, because you have an x and a y where the y hasn't been isolated, so it's a different type of equation. I believe they might be called parametric equations when that happens. I'm forgetting the term, but anyway, that kind of graph is often not a normal type of graph, so I can't visualize what it's like. I'm not even sure how I would input that in Desmos to see what it would look like, because, I mean, theoretically speaking, we'd have another y on this side, so I'm not sure exactly what would happen. I think we'd have to isolate y, and then there'd end up being a square root there, okay? But it's weird when you have an x and y, but that just happens to be a theoretical example instead, okay? So unless we have more information to be able to graph it, that's all we can do with that one. So let's take a look at this one. Sorry, let me go back here. I don't want to go too quickly. I'm forgetting that there's a bunch of people listening to me right now. Are there any questions about this example? Okay, I'm going to assume we're good to go. Let's take a look at this one. Oops. I'm not sure why it keeps doing that on me. So this is an interesting one. Let's just factor out the bottom first, because we can see that it can be factored. Okay, and we'll see what happens after that. Some of you may already notice that there's going to be another issue. Let me get that. So what is our restriction going to be? Well, following the technique that I've talked about for a few times now, we'd say that a can't be equal to, change the sign of the constant, positive 1, over the coefficient of a, which would be 2. Now, I purposefully made this one a little bit tricky, so be very careful here. There's a problem because the 2a is positive, and here the 2a is negative. The the 1 is negative, the 1 here is positive. Can you see that they're in the wrong order? All right. So I'd like to make it so that the 2a was first and the 1 was second. Now, if I go off to the side for a second, if I rearrange them right now, and here's a very common mistake that I've seen multiple times as well, where a student will keep the negative between the two terms and not move it with the term that it's attached to. So the 2a is actually negative because that minus sign means you're subtracting or taking away 2a. So 2a has to be the negative part of that expression at the top. The 1 is positive, so it has to remain positive if I change them into their proper order. Okay, and usually proper order. When you have a negative term, often we will write it second, okay? But I'm trying to match it to the bottom here where the 2a is the first term, right? But these are still not the same. I can't just cross that off. They have the wrong signs. So chat, what do I do? How do I fix that problem? Wow, somebody's already answered. Okay, that's correct. If we factor out a negative 1 from the top, okay? If we factor out a negative 1, oh yes, we could have done that on the bottom as well. If we had factored out a negative 2 on the bottom, but we're trying to avoid negatives on the bottom, okay? So that's why I didn't do that. If you factored out a negative 2, you'd have that, it's not a big deal. You'd have to move that negative up to the top, but it's actually seen, I think, as a better technique to factor it out of the top instead. So if I factor out the negative 1, and looking at what I did up here, I'm not going to do 2 steps here. I'm just going to do it all in 1 step, okay? I'm going to move the 2a first, but it's now going to become a positive 2a because I factored out that negative 1. And I'm going to move the negative 1 second so that I can have it in the right position. And it was positive, and now it becomes negative, over 2 times 2a minus 1. And now I can cancel out because everything is multiplying and dividing. So that cancels out with that. And we're left with a very interesting answer here. We're left with a constant. So this was originally a algebraic expression with variables in it, and when we simplify it, it actually is a constant. So if I replaced all of the a's by x's, right, and I asked you to graph y is equal to negative 1/2, what kind of graph is y is equal to negative 1/2? This often messes students up as well when you ask them to graph. In fact, the question on your assignment recently that said one of the lines was y equals 0, I wonder how many people didn't understand that that was a horizontal line. That is correct. When you have a y equals a constant value, that's telling you that you have a horizontal line at that value. So let's say that 1 is, or negative 1 is here, okay? However, at an x value of 1/2, at an x value of 1/2, I have an open circle, okay? Because that's what my restriction is telling me. So I hope I'm not spending too much time explaining that, but the link between the two is quite important to be able to see in your head, oh, what kind of graph is that, when you can. What does the restriction mean? And if I'm not mistaken, we're almost done. Like I said, today's lesson is not really that long. There's 2 more examples to do. So this is just another example very similar to the one we just did. There's only one factoring that makes sense here. The bottom is already in its simplest form, so I can immediately write the restriction. The top is not in its best form because I want it to look more like the bottom. So I'm just going to factor a negative 1, just like I did before. The x is going to become positive. The 9 is going to become negative. And now I can simplify those two. And here's another case where we end up with just a constant value once that's done. So it's a horizontal line that has an open circle at x equals 9. And I don't know if you can start to understand. This starts to mean that with math, we can represent pretty much any weird graph that is like an experimental result. Okay, some sort of experiment is done. We end up with this weird open circle at one spot of the. Like, think about I usually use this example. Imagine you're doing some sort of psychological testing on a bunch of people as a psychiatrist, and you end up with one person who's not following the same pattern as everybody else. That could be that open circle. I don't even know if that's a legitimate example, but I'm just trying to say, like, where could that happen, right? So we don't only analyze mathematical and scientific properties with graphs and equations. We sometimes do it with other things too. So if you needed an open circle in a certain part of the graph, then you could control it by doing something like this. Okay, this example I'm going to present as kind of more of a introduction to tomorrow's topic. I just want your brain starting to think about this. How would we go about multiplying these two expressions? And we also have to state the restrictions. Now, the first thing I want to make sure everybody understands is you do not need a common denominator here. This is a multiplication, so you're just doing top times top and bottom times bottom. But there might be a better way of writing it if we take into consideration that we need to find our restrictions as well. And what I'm heading towards, and I'm hoping you can see it, is we have two quadratics here. Trinomial quadratics. Can we factor those trinomial quadratics? If we do that right away, it's first of all going to allow us to tell what are our restrictions. And secondly, it might allow us to actually cancel out some of the brackets that are going to appear once we've got it factored. Right now, we can't see anything simplifying. Okay? There's nothing that exactly matches the bottom counterpart, so we can't cancel anything out. So let's factor the top and bottom. And now we're doing type 1 quadratics, folks. Again, I'm making a plea to those of you who insisted on doing decomposition a little while ago. If you had two type 2 quadratics and you had to do decomposition for both of them, you're going to be significantly slower than somebody who knows either the trial and error method or the way that I showed in class for doing factoring. So I'm really asking you to consider going back and watching my videos on how to, if you don't know how to do my method or the trial and error method, go back and watch my videos on how to do my method. Okay, because I really believe that you're going to slow down so much by having to use decomposition here that it's going to be an issue. Okay, so now these are type 1 quadratics, so it shouldn't be too hard. We need two numbers that multiply to -6 and add to 1. Notice I'm not writing it down anymore because we shouldn't have to for a type 1. You should be able to, in your brain think, what are two numbers that multiply to -6 and add to 1? Now, if you do need to do it, please do so. I'm not trying to say it's bad to do so. I'm just trying to push you to maybe try to do some more mental mathematics here, okay? So what two numbers multiply to -6 and add to +1? Well, I'm assuming it's going to be 3 and 2. Okay, one of them has to be negative, and that would be the -2. Okay, so we're going to have x plus 3, x minus 2. On the bottom, we need two numbers that multiply to -15 and add to 2. That would be 3 and 5. One of them has to be negative. I believe the 3 is negative. Okay. Let's state our restrictions. There are three numbers that x can't equal to based on those three brackets. One of them is going to be negative, two of them are going to be positive. So if we try to figure that out before, we can write them in the proper order as well. So x can't equal to negative 5, x can't equal to positive 2, and x can't equal to positive 3, which I'm just getting from those three denominators. Before I combine these, it's top times top, bottom times bottom. Now, if this had been an x plus 3, we could have joined it together with that x plus 3 as an x plus 3 squared, but it isn't. Okay, so nothing combines here. We do not want to re-expand, we just factored. So what we're looking for is, does any top thing cancel out with any bottom thing? Well, you don't have to group them together before you do that. And I've been also trying to show this every so often throughout the year as it's cropped up. If you have a fraction multiplied by another fraction, this x minus 3 is considered over that x minus 3, because it will be placed there if we do top times top. X minus 2, same thing. I'm going to do a double line through that one so you can see what's been canceled in the note later on. Okay, the x minus 2 and the x minus 2 will cancel. So it just saves us all that writing of having to do the top times top, bottom times bottom, when you can just cancel them out as they are. And what are the only two brackets left? The only two brackets left are x plus 3 over x plus 5, and we are done. So like I said, that is going to be it for today's lesson. As you can see, I do have a bunch of homework questions ready to assign to you. Now, folks, what I'm planning on doing is actually giving you the whole period tomorrow to work on those homework questions. Okay? Just to keep the pace at a more manageable level, especially since you have other courses going on too, and I have to keep that in mind, which I hope I have been. I hope I've been giving you ample time to do the work, but it just happens that this week I'm actually able to give you a little bit more time. So I will post those questions on the Google Classroom, but I'm planning on giving you the period tomorrow to work on them. I can definitely be available for Google Meet tomorrow. So I'm just going to stop recording here, folks. So I'm just going to say bye for the recording. Goodbye.